Hey, here's a video key to our recent circular motion quiz. This is kind of a messy copy because this is the one I was using as I was writing it and making various forms. But keep in mind that the number sequence was scrambled and so were the choices. So make sure you don't pay too much attention to question number or alphabet letter of the correct choice. One of the problems involves a car going around a circular curve on a horizontal road at constant speed, and the direction of the frictional force has to be inward toward the center of the circle. So if the circle is shown, it looks like that, kind of the pizza view from the side. This is how the car appears if you are behind the car, so looking at the back bumper of the car. You can see that force is pointing left because this particular car is circling that away. So the only statement here that's true is that the car has to be moving because there's a force that is perpendicular to the curve and inward. So if I draw it from map view like this, the velocity at any point is tangent to the circle. So that'll keep changing as things go around. But the centripetal force is always directly inward, and so too is the centripetal acceleration. So that has to be the sum of all forces if you're going to have circular motion. And so we don't typically draw that as its own vector because it's something specific. In this case, it's friction. Choose 2 on this one. Mark both correct choices. The direction of acceleration, which we just drew, is perpendicular to the velocity vectors because acceleration is straight inward. It's directly proportional to net force. So inward toward the center and perpendicular to velocity. This car moving around a curve has some specific numbers given for you to calculate the actual magnitude of the frictional force. And I was nice and pointed out that, hey, there are kilometers there. You do have to know the metric system because they will sometimes give you things in kilometers and centimeters, and you're going to have to watch for units as you go. So to get the magnitude of the frictional force, I have to recognize, hey, I've got a free body diagram here. Hey, there's a net force statement. This looks familiar. So when I substitute in mass times acceleration, I substitute mass times centripetal acceleration. So here I am with mass, velocity squared, divided by the radius, and that's the correct answer. Then there was an airplane on a string. I actually have one of those sometimes, or I have had, and it sometimes flies in a circle around our classroom. You're given a bunch of extraneous information that you don't need, including diameter in centimeters and mass in grams, but they're asking for periods. So all you really need is the time it takes to make some circles, because that allows you to calculate the time for exactly one circle. So 13.6 seconds is the numerator, 10 revolutions or circles is the denominator, and therefore we have an answer that has a unit of just plain seconds at time units in the numerator. So that's 1.36 seconds. Pretty easy one. Just looked a little scary. Here we have an algebraic one, chance to let your algebra skills shine. If you have a bicycle ridden in a circle with radius r at a speed v and a centripetal acceleration of a, or ac, what's the acceleration if you start changing things and you double your speed and ride in a circle with a different radius? A radius, in fact, that's triple. Sorry, you can see I fixed this before you actually took the quiz. So I write the basic guiding formula. So since these are the criteria I've been given are the actual algebra symbols in the equation, that's my original centripetal acceleration. So my new one is going to have that doubled velocity. And remember, the new velocity, whatever it is, gets squared. And the denominator is going to be the new radius, which is triple the old one. So when I do the math on just these coefficients I put in contrasting colors, it's 4/3 bigger than what I had in the first place. So the 4/3 is what I want in that answer right there. 4/3 times my original centripetal acceleration. This problem had a toy attached to a string, whirled in a circle, and we want to know the maximum speed the toy can have without breaking the string. So here we go again. This would be like a sideways circle, like a pizza, viewed from the side right here, okay, as it circles. So the net force has got to be coming from tension because that's the only thing in the plane of the circle. The net force is mass times centripetal acceleration. And when I solved for that, I actually chose to round differently than I ordinarily would. I didn't want to round up because I don't want to go over the maximum speed. So if you got 26.5 on your calculator, don't be surprised. That's fine. That's still clearly the correct answer. Okay, this one I messed up on. Period 1, 2, and 3. I think you can see why. I had kind of a zoo of different numbers that I was working with. So for period 1, 2, and 3, I omitted this from the calculations in Skyward. So it's as if this problem did not occur on your quiz at all. You can see it though if you look on it in Aware, just don't be concerned about it. It didn't count for you. It did count, however, for periods 4, 6, and 7, because thank goodness a student finally told me about it. So I thought it was kind of interesting. Nobody in period 1 or period 2 mentioned any problem with a test or quiz question, I should say, that did not have a correct answer. But anyway, let's see how we solve this. This is a speed bump, which means you're going over the top of a circle and you're going right side up. Your weight is down towards the center of the circle. Toward the center is positive. That means the normal force, the road lifting the car up or the seat lifting you up, that's away from the center of the circle and therefore it's negative. So I sum the forces that are in my free body diagram. Not a perfect free body diagram because I drew the circle, but if I had a perfect one, there'd be no circle there, just a single object. So solving for the normal force, it's going to be the weight minus the net force. So mg minus mv squared over r. And then I put in the numbers that I've been given. A 50 kilogram passenger, so mass twice, and then a velocity of 8.7, a radius of 3 meters, and I get 772 newtons. Okay, 772 newtons is not shown on this because this is the bad old printout. But for period 4, 6, and 7, there is a correct choice of 772 newtons. Sorry about the mess. Okay, like I said, it didn't hurt you a bit. Okay, here is planet Quaoar. It's 3 times as massive as Earth, and it has a different radius. What would the weight of an astronaut be? So multiple step problem. So first thing I have to figure out is that algebra is going to make this easier than actually plugging in all those numbers. So I'm not going to bother to put in 6.67 times 10 to the negative 11. I'm just going to compare this equation that we have for little g. Little g equals, that is gravitational acceleration equals, the gravitational constant, the mass of the planet or sun at the center of the orbit, and then dividing by the radius squared. And this came about, remember, because we said weight is mg, but weight is also gravitational force. So when we set them equal to each other in your notes, I showed you how to make this formula for calculating g that works on any planet, moon, asteroid, anywhere. I'm calling it g prime, just to remind myself it's not Earth's. So if I put in 3 times the mass and 4 times the radius, I'm careful to remember that the whole new denominator is what gets squared. So this is 3/16 of what I had in the first place. If what I had in the first place was Earth's, it's 3/16 of 9.8. Okay, so now I know how to figure out the weight of this astronaut. Weight of the astronaut is going to be mg. So the weight on the other planet, g on the other planet. So it's 67 kilograms times 3/16 of 9.8, and that's how I get a weight of 123 newtons on planet Quaoar. Okay, here we have a moon, and we're asked about orbital speed. So here we played a different set of equations against each other. We realized that this is centripetal force, and this is gravitational force, and gravitational force is the centripetal force for things that are in orbit. So when we set those equal to each other in your notes, I showed you how to do that, cancel things out, so that you get an equation that says v squared is big G, big M divided by R. So take the square root of that to get the actual velocity. Okay, so what have we changed? Well, it's got the same diameter, which means it's going to have the same radius, but this planet has just become more dense and now has twice as much mass. So if we sneak a 2 in there, notice I spread out the equation so I can visualize sneaking something in there, so doubling the mass. I have everything I had before, except there's also a square root of 2. So it's the square root of 2 times the velocity that I had before. These algebraic approaches are super important, very common on the multiple choice portion of the advanced placement exam, and also they're real time savers. Okay, radius of the Earth, a satellite in circular orbit. What is its acceleration? Notice I don't know period. The Earth I know the period of, but I don't know how fast this satellite is moving or how long it takes to go around. And I just want to remind you that we have our centripetal acceleration equation of v squared over r. All right, and we also have this one, which we just used, of velocity for orbit, as you can see right up above. So if I just go with that equation right up above, there's big G, there's the mass of the Earth, and now I need to divide the satellite numerator by the correct radius. So draw a picture. It's going to be the radius of the Earth plus the distance above the surface. So that's what you can see here. So there is the distance above the surface. There is the radius of the Earth as given in the problem. And so I just plug and chug in my calculator and I get 4.3-ish meters per second squared. Okay. All right, don't worry about that. That was just notes about changing for versions. The reason an astronaut on the International Space Station feels weightless is astronauts in free fall because they're in orbit. And Isaac Newton taught us that orbit is the same thing as falling. All right, so 11 questions so far, 2 more to go. A particle in uniform circular motion. Ooh, I have a period, I have a speed, and they want to know the radius. So if I list those things, that helps me see which equation I want. I want an equation with those variables and nothing else. So if I put that in, do a little algebraic rearranging, there's my formula for the radius. So the period goes in right as it is, 0.24 seconds. There's the speed right there. I divide by 2 and pi. So remember, if you're multiplying times 2 pi, open a parenthesis there. And now I get my answer. And it's not one of those choices. So, hey, did you notice units again? I was given speed in meters per second, but I am given this radius range of choices in centimeters. So 0.16 meters is 16 centimeters, and that's the correct choice. Here you are. Imagine that you're driving on ice. Okay, so you've been trying to make a circle. You've been successfully making a circle, and all of a sudden you hit the big patch of ice. That causes the force of friction to become 0. So what that means is there's 0 centripetal force. If you have no force inward toward the center of the circle, you have no circle. So you're going to go flying off in straight line motion, tangent to the circle. Okay? In other words, in the direction you were headed at the moment that you hit the ice. So if you hit the ice here, you go that way. If you hit the ice here, you go that way. So the choice that's correct is moves along a straight line path in the direction it had when it first hit the patch of ice. All right, so there you go. That's a really good quiz to study because that stuff will be not only on the AP exam in May, but also on our upcoming final exam in December. Thanks, everybody.